All right, let's continue on. Let's go to number 19. For number 19 here, how many valence electrons are in group 17? So that's a pretty straightforward one. What we're going to do is we're going to use this method. For group 17, we are literally going to do group 17. We're going to subtract 10 from it, and that means that we've got 7 valence electrons. So that would be 7 valence electrons there for number 19. What does chlorine need to do to become stable? Well, if we look at chlorine, let's kind of take the path that we're going to be able to do the following. Let's go ahead and bring up a periodic table. Let's find out how many electrons. And let's just go ahead and create two things, the electron configuration and the Lewis dot structure, so that we can see what we're talking about when we're trying to get this thing about stability. All right, so let me go to do that here, and I'll bring it up on the screen, then we'll do it. So here is chlorine. Chlorine is number 17. So if we get the configuration for chlorine written out, that'll be a good start. So why don't we do that next? Let me put that on the screen, and then we can continue our discussion. Okay, so here is the completed configuration for chlorine. Chlorine has 17 electrons, so that's 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. So the part that we're interested in is the part with the highest orbital number. So notice here we've got 1, 2. So it's the first orbital, second orbital, and these threes here and here for the s and the p's, this corresponds to the third orbital. So these electrons are the electrons that we're interested in. So if we add up these two numbers together, 2 plus 5 gives us a total of 7 valence electrons. Now remember that an octet is what provides stability. So if we take the difference here, 8 is the octet, and if we subtract 7, that means that 1 valence electron is needed in order for us to have stability. So when we look at the question, what does chlorine need to do to become stable? It needs to acquire 1 more electron. It's going to go in the p orbital because it has space for 1 more electron, but it needs to acquire that electron in order for it to become stable, because at that point it will have met the octet. Right now at 7 valence electrons, it's 1 electron short. So if we put that here as a response, then we'll see that answer there. Let me go ahead and put it for you so you at least have a record of it. So there is the written statement of what chlorine needs to do to become stable. Moving on to question 21, how many electrons will chlorine ion have? Well, currently when we look at the configuration for chlorine, chlorine as represented on the periodic table has 17 valence electrons. So let's kind of look at what this really means. So for this configuration here, I'm talking about this configuration here, right there. Right now, the pen count is going to be, the proton count is 17 and the electron count is 17. Protons are positively charged, electrons are negatively charged. So if I come in here and I add these two numbers, right now it's going to have a 0 charge. But if the chlorine atom accommodates or fills the octet that it needs over here, if it gets another electron to become stable, yes, it will get 6 electrons in the 3p suborbital, but when it does, the balance between protons and electrons, it's no longer going to be 0. At this point, the proton count is going to be 17, but the electron count, if it were to get that additional electron, means that it will have a total of 18. So if we put in the charges plus for protons, minus for the electrons, the charge would become, here, let's write it at the bottom, it would become a -1 charge. That's what would happen here if the chlorine were able to acquire that. And when it does, it becomes an ion. So the charge that it would have, or how many electrons will it have? It would have 18 electrons. Number 22 seems to not be on the page, but let's keep going to 23. Let's take a look at the next question here. What is the charge of an iron atom with 24 electrons? So let me go ahead and get rid of some of this work here so we can show it, and then we'll do the work for iron. All right, so iron, when we bring up the periodic table, let's go ahead and bring this up here. Iron is located down here. So it's got 26 electrons. So let's go ahead and get its electron configuration. We'll put this down here at the bottom, and then we'll get the configuration on the screen for you. All right, so here is the configuration for iron. So since iron is right here, number 26, it's in the 1, 2, 3, 4th orbital, 3D, 1, 2, 3, 4, 5, 6. That's why we represented it here as 3D6. But notice here the electrons here is 26 electrons. The question is asking us, what if it has 24? Well, a neutral atom here for iron, the proton count is going to be 26 and the electron count is 26. So when we look at that from a positive-negative stance, positive and negative, that means here the charge is a zero charge. But what the question is asking us to consider is, what if it has 24? So that means that this 26 value, we need to change that. If that were the case, let's just go ahead and write it down below. If the proton count is equal to a 26, but the electron count is equal to a 24, then we have a difference here. We've got 2 more protons than we do electrons, so that means here that the charge will be a plus 2. So when it asks us what is the charge of an iron atom with 24, a neutral atom will have 26 electrons. So when you have 24, you're going to have 2 electrons short of 26. So the charge here is going to be a plus 2. All right, so there's that. Let's go ahead and take a look at 24 and 25. What I'm going to go ahead and do here is I'm going to go ahead and define these for you, put them on the screen, and then I'll explain a little bit about that. All right, so here are the 2 definitions. The definition for a covalent bond is the following. A covalent bond is a bond formed between a nonmetal and a nonmetal. So you have 2 nonmetals. So if you have true, pure nonmetals and it's the same atom, then the difference is 0 when we look at the difference in electronegativity. But mathematically, the electronegativity difference between the 2 bonded atoms, if there is a difference, the difference is going to be less than 0.3 on the scale. For an ionic compound, or rather an ionic bond, all right, had to edit a little bit here. There was a little bit thing here, but here's the corrected version. An ionic bond is a bond formed between a metal and a nonmetal. And mathematically, if we're looking at it from the electronegativity difference, the electronegativity difference between the 2 bonded atoms is going to be greater than 1.8. The easier way to find it is just make sure that you understand that if a metal binds with a nonmetal, that's typically going to be ionic. But you may need to do the calculation if the atoms are closer together on the periodic table. All right, number 26. Let's go ahead and define electronegativity and explain how it relates to bonding. So in a very short way, electronegativity is the following. So the electronegativity is the following. I've already gone ahead and defined it for you. I'm going to put it down here at the bottom. But electronegativity, in a brief way, is nothing more than the ability of an atom to take electrons from another atom. You could also say that the electron is able to attract electrons to itself, and the atom that has a higher electronegativity is able to do that. So if you have a condition where you have 2 atoms that are going to bond, so this is how it relates to bonding. If one of the atoms has a higher electronegativity compared to the other one, then that particular atom is able to take the electrons away from them and it creates an ionic bond. But if the electronegativity difference between the 2 atoms in question are close to one another so that the difference is less than 1.8, then they're more likely to share those electrons, in which case they're going to form a covalent bond. Not a bond, but a bond. So let me go ahead and correct that here. That's a bond there. All right. So I'm going to go ahead and erase some of this stuff, move everything up so we can finish up the last couple of problems here, 27 through 29. All right, in question number 27, we're going to write a formula for the following compound. So they want us to write an ionic formula for aluminum sulfide. So what we'll need to do is to look for the symbols. Aluminum is in group 13, so it's going to be a transition. It's only got 1 charge, so if you go look it up, you'll find it. So let me bring that periodic table of ions to the screen so you can reference it, and then we'll go from there. So here is the periodic table of ions. We're going to go to look for aluminum. If you look for aluminum, aluminum's right here. It's going to have a +3. So the first thing we'll do for the aluminum up here is we're going to go ahead and press or identify the charge. So we're going to say +3. Then we're going to look for the sulfide. Notice it's IDE. That means it's monatomic. So we're going to go look for the monatomic sulfide. IDE also says it's the negative part. So we're going to look over here in this region of the periodic table. And sulfide's actually right here. It's a -2 charge. So what I'll do is I'll put a -2. The next thing that I'm going to do is come back and write down the symbol. So notice sulfide is the symbol is S and the aluminum is Al. I'm going to go ahead and write these down. So this is going to be Al and this is S. And now what I'm going to do is take a look at the charge. And so with the charge, notice I've got a 2 for the sulfide and a 3 for the aluminum. And all I'm going to do here is crisscross. So I'm going to bring the 2 down and put a 2 here and bring the 3 outside and put a 3 down there. So my final formula, if I'm writing that formula down, I'm going to go ahead and let's use purple here to distinguish. I'm going to have a formula here of Al2S3. And there is my formula for the aluminum sulfide. I'm going to go ahead and do the same thing here for the covalent compound dinitrogen trioxide, except here with covalent compounds, what we do not need to worry about is we do not need to worry about charges because it's a covalent. All I really need to do here, if I'm using the rules properly, is just make sure that I translate any prefixes. So I've got a prefix here of di, I've got a prefix here of tri. So begin by translating the prefixes. So the di means 2, the tri means 3. Then we translate the respective parts. So the first part here is going to be the cation, because notice it's just the name of the element. But notice the IDE, that's what tells us it's the negative part. The symbol for nitrogen is simply N. Now, if you make the decision to come over here to the periodic table of ions, you would definitely see here that it says nitride. But the thing that you need to remember is that these elements here are represented by name if the element has a negative charge. In this particular case, it says nitrogen, so we have to use the regular periodic table. And so in this particular case, the symbol for nitrogen is simply N. Oxide, we do need to use the version here that is identified here. So the symbol for oxide is O. And so here in this particular case, we will put O for the oxide. And then we want to put these exponents 2 and 3. We want to put the exponents just underneath and to the right of both the nitrogen and the oxygen. So let's go ahead and write the formula up here in the spot that's provided. So the formula here should be the following. It should be N with a 2, O with a subscript 3. And so there is the formula for dinitrogen trioxide. Now we move on to 28. We're going to name the following compounds. They're providing us formulas. Here's an ionic compound with a formula and a covalent compound with another formula. So let's begin with the first part. Notice here we've got 2 different atoms. And what I can do here, just to illustrate the way I've done it in class, the first part is the positive side, and the other part, I circle the entire thing, and it's negative. The thing about the positive portion, notice we've got 2 different atoms, so that makes this positive portion a polyatomic, and you know that it's a polyatomic because you see parentheses. The parentheses tell you that these 2 atoms are bonded together, and there's 2 different atoms. So when we go look for the name of this particular thing, we want to go to the polyatomic section, which is at the top of the periodic table of ions. And since it's positive, that section is going to be down here at the bottom. There's only 2 of them identified, one of which is known as ammonium. So if I'm going to get the name of this, I want to name this one, and it's going to be ammonium. Now, before I move the periodic table out of the way, let's go look up this PO4. It's also a polyatomic, and we're going to look in the polyatomic section, but we're going to begin with the P in the formula. It's PO4, and the name for that is phosphate. So we're looking for ammonium for the positive, phosphate for the other one. So let's go ahead and put the name down here. I'm going to go ahead and move this periodic table out of the way. and come in here and provide the name, which is going to be ammonium phosphate for the ionic compound. Now finally here we're naming the compound here covalent, and so when we name covalent compounds there's a very specific nomenclature form. Let me see if I can get that on the screen for you so we can follow it, and then we'll go from there. All right, so here is the rule. We're going to be naming compounds. It's going to be case 4, and it says that you want to do the following. Let me zoom in a little bit more on this so we can see it very clearly. What we want to do is we want to get the prefix of the first atom, followed by the name of the cation, followed by the prefix of the second atom, and then followed by the name of the anion. So let's go ahead and do that process and include the name at the bottom. So carbon's name is going to be carbon. There's only one copy. You can see that there's no number written, so we assume there's a 1, so that would be mono. We don't use the word mono, but we do put the name carbon, so let's go ahead and put that. So this would be carbon. And then we look at the second atom, and there's F, but there's 4 copies. So the prefix comes next, so that would be tetra. And then the name of the anion, so in this case we've got fluorine or fluoride, because we look over here on the periodic table, it's fluoride. So we put the name of fluoride at the end here. So I just move the periodic table over to the side, so this would be tetrafluoride. And that would be the name of this covalent compound. Now finally, how do we define metallic bond? Well, a metallic bond is defined the following way. Quite simply, a metallic bond is a bond that's formed between a metal atom and a metal atom. Keep in mind that in metals, the electrons are shared throughout the entire metallic structure. So all of the electrons in a metal sample belong to all of the atoms in a metal sample. But in simple terms, the bond is between a metal atom and a metal atom.